Here, hold on.
Great, thank you. So I'm thrilled to be here. I appreciate your attendance. Looks like we're going to have a big crowd. Desiccant dehumidification, or just dehumidification in general, is going to be the topic of conversation today. My name is Dave Shirk. I'm National Sales Manager for Innovative Air Technologies out of Covington, Georgia. We're just a hop, skip, and a jump from Atlanta. So any of you in the area that would like to come over and visit our factory sometime, please do. In fact, I'm going to show you a very short video here in a second. You'll get a look at the factory, you get a look at the product, yada, yada. I think, pictures worth 1,000 words. Videos are worth even more. So I'll start with that. But I will introduce myself again, Dave Shirk. 45 years in the industry. I've worked for three of the largest manufacturers of HVAC equipment and solutions in the world over that period of time, as well been a desiccant dehumidification rep. Now I am a national sales manager for a desiccant dehumidification manufacturer, and I love it. I love Psychrometrics. I love dehumidification. Been doing it a long time. I'm an ASHRAE Distinguished Lecturer. I'm an ASHRAE Life member. I'm an instructor for ASHRAE's Humidity Control Courses 1 and 2, and if you're coming down to the AHR in Orlando, I'll be teaching 2 days, 3 hours each on dehumidification. If you want to hear more, love to have you come. What I'm going to do now is tee up a real quick video. This worked before. Terry, again, you will tell me just a quick yes that you are seeing this full screen and hearing it. And in 3 minutes, this will be over with.
Welcome to our
You good?
manufacturing facility. Today I'm going to take you on a guided tour of one of our solid desiccant dehumidification units. I'm going to start on its inlet, I'm going to work my way through its outlet, I'm going to talk about every component, and I'm going to tell you what it does. So come on, let's get started. We're starting on the process inlet side. This unit happens to be an indoor unit, so you see a duct attachment, and it could be a unit that would be located outside. In that case, this inlet would typically have a hood and a damper assembly. Our next component in direction of airflow is some type of air filter. This happens to be a MERV 13 filter, but could be any type or efficiency specified by the end user. The higher the MERV rating, the more efficient it is at extracting smaller sized particles from the entering airstream. As we continue our journey, we see a pre-cooling coil and a drain pan. This coil could be either chilled water or direct expansion, depending on the specific project requirements. Our next component is the desiccant wheel and the heart of our dehumidifier. It consists of a circular substrate material, usually made of fiberglass, aluminum, or ceramic. It is constructed with fluted passages through which air can flow. The substrate is impregnated with silica gel, and as humid process air flows through the wheel in one direction, it encounters the desiccant. Water molecules move from the air into the silica gel to be adsorbed and removed in the process. You may notice a small bypass duct and damper located directly below the wheel. This provides a downstream mixture which can be controlled to the environmental set point of the indoor space, enabling the unit to maintain precise dew point temperatures or relative humidities. From here, the process air enters a fan assembly and is discharged through the end of the unit into field-supplied ductwork, which conveys the air to the environment to be controlled. We move now to the opposite side of our unit. It is important to note that the wheel is continuously rotating between the process and reactivation sides of the unit. You can see an air opening and damper from which we will bring in outdoor air for the purpose of reactivating the wheel. This airstream may be elevated in temperature to somewhere between 120 degrees Fahrenheit to 285 degrees Fahrenheit. This allows the adsorbed water molecules to break their bond with the silica gel and be removed. The drier the wheel, the more moisture which can be adsorbed in the process side, and the lower the dew point temperature delivered to the indoor space. We move on to the reactivation air outlet, where the air leaving our unit at this point has been slightly cooled due to what is known as the latent heat of vaporization, but it is loaded with moisture at an extremely high dew point temperature. So that concludes our tour of one of our solid desiccant dehumidification units. If Innovative Air Technologies can support your needs when it comes to dehumidification, please reach out to us at any time.
All right, so I thank you for indulging me. I got to figure out how to get out of here. Hold on, there we go. 1 minute. There we go. And I'm going to pull over my slide deck and open that. All right, one more time, Tracy. Are you seeing full screen Innovative Air Technologies, and are you hearing me okay?
Yeah, everything looks great.
Wonderful, thank you. So enough on the company. I think, I've kind of told you who we are and what we do and where we're at. Come see us. Enough on me as well, right? You know how to get a hold of me. Holden and team. Our company has been in business in actuality since the late 1980s. The gentleman on the far right is Jerry Orr, the founder of the company originally. His son Casey took it over in 2001, rebranded it, renamed it, rebuilt it, kind of put it on steroids. And it is today what's known as Innovative Air Technologies and has been called by that name since about 2001. But our roots go back quite, much further than that. Let's talk a little bit about what a desiccant is, because we're talking about desiccant dehumidification. A desiccant is simply a substance that is hygroscopic. It has an affinity for moisture. It's moisture seeking. It loves moisture, like a sponge, only not a sponge. We use silica gel as our desiccant in our dehumidifier units. And you're very familiar with silica gel. Up here on the right-hand side, you see the little packet. And if you've ever ordered anything, excuse me, perhaps on Amazon, and you've had it shipped to you from point A to point B, where you receive it, and you open the box up, and it's a product that is hygroscopic as well, that might absorb moisture or be damaged by moisture during shipping, you'll see that little packet in there. And once you open the box up and you take the packet out, you do as you're instructed. You don't eat it. You could if you want to. It won't kill you. But you throw it away. And you throw it away because what it has done from where it was put in the box to where you have received it is dry the air in that box. It is full of silica gel. Silica gel is an adsorbent. The silica gel, because it's put in the box when it's dry, is at a very low internal vapor pressure, which means that as it takes its ride to your front door, it is adsorbing moisture from the air in the box, which is moist and at a higher vapor pressure. Vapor pressure travels from high pressure, moist air, to low pressure, dry air, dry desiccants, for example. So that adsorbent is constantly sucking the moisture out of the air, keeping the product dry and holding the moisture in the pores of the desiccant as a water molecule, never condensing and never getting wet in a traditional sense. It's loading with moisture, just like a sponge would load with water, but no liquid, right? This is pretty cool stuff. So by the time it gets to you, it's so small, it's full of moisture. It's holding all the moisture that it can. It's not wet, but it's full of molecular water molecules. So you do as you're instructed. You throw it away. It's done. The sponge is full. Here's a little secret. If you were to take that packet, put it on a cookie sheet, stick it inside your oven, hit it with a little bit of heat, you would increase the temperature of the silica gel. Don't start the package on fire. It's paper, right? But you would increase the vapor pressure of the moisture in the silica gel to be above the vapor pressure of the air in the oven. And based on higher vapor pressure water molecules in the desiccant and lower vapor pressure water molecules in the air in the oven, it would allow the desiccant to regenerate, desorb, spit off that moisture molecularly into the oven air. And you could then take the desiccant packet out. The desiccant would be dry and you could use it over again. And you could continue that process. Load it with moisture, stick it in the oven, heat it up, dry it out, take it out, use it again. Adsorbing moisture, high pressure to low pressure in the desiccant, desorbing moisture, high pressure in the desiccant, low pressure, vapor pressure in the air in the oven. And you have a continual cycle, right? But in practice, in the real world, in the field, that's a little cumbersome. Every time we load our desiccant up with moisture to pull it out and have to put it into an oven and heat it up and bring it back. So what we do is we put the oven in the unit. Simple. And we create a process that's continually adsorbing and desorbing moisture continuously. And I'll show you how that works in a minute. But quite honestly, it's a thermodynamically eloquent way and a simple way to dehumidify the air. That's how we do it. More on that in the slides to follow. Now, I'm locked up. Bear with me. There we go. I think it's real important that we quickly differentiate. I'm trying to get my mouse to work. I'm hoping you're seeing my cursor. Differentiate a little bit between how traditional air conditioning systems dehumidify the air and how desiccants work. Now, what we see here is what I like to call, and this is long-winded, so bear with me, a traditional refrigerant-based cold surface air conditioning system that dehumidifies the air as a byproduct of its temperature. Oh man, that was a lot to say, but I'm going to unpack that here for you in a minute. On the right-hand side, we see a traditional cooling coil. It's made of copper tubes and aluminum fins through which I will pump some type of a cold fluid or refrigerant. It might be direct expansion, R410A or whatever. It might be chilled water, right? And based on the temperature of the refrigerant or fluid that I supply to the coil, I will create a certain coil surface temperature. The colder the fluid coming in, the colder the surface temperature, the more I can cool and dehumidify the air in this type of a system. So let's look at how it might work. Let's say this is a DOAS unit, 100% outdoor air, bringing in warm and wet air from outdoors and cooling it and providing it to a space. And we can see as I take that warm and wet air through my coil, what I end up with on the other side is cool and dry air and moisture condensation typically forming on the fins, falling into the drain pan and being removed from the building. And that's how I dehumidify the air in a traditional cold surface condensing type system. Let's look at it on the psych chart. Point A might be air coming in at, let's say down here, dry bulb temperature wise around 100 degrees Fahrenheit, something like that. Who knows, right? And on the right-hand side of the chart, we see grains per pound or the amount of moisture in the air. And it might be at, let's say, 130 grains per pound. Now, my guess would be, your dehumidification design day conditions, grains per pound are probably 140 or more. So this is a little light with regards to what you might see down in your neck of the woods. But the point will be valid regardless of what we talk about. Now, I'm saying around 130 grains per pound of moisture coming in. What does that mean? Well, that's pretty darn humid air. There are 7,000 grains in 1 pound of water. So what this is saying is for every pound of air, I have 137 thousandths of a pound of moisture in that air. Doesn't seem like a lot, but we know it can wreak havoc on buildings if it isn't dehumidified properly. So I'm going to take that air from point A, I'm going to run it through my cold cooling coil, and I'm going to cool it down. And we can see sensibly I'm taking that air from maybe 100 degrees Fahrenheit and 130 grains per pound down to about 55 degrees Fahrenheit, 55 degree wet bulb, 55 degree dew point, and maybe 63 grains per pound, something like that. So I have cooled the air sensibly. I have reduced the amount of moisture in the air. I have hit saturation over here on the psychrometric chart, and I have condensate forming. And I'm removing moisture based on the temperature of the air leaving the coil. Now, that's great if I want to maintain a space somewhere between 50 and 60% relative humidity. By the time it comes back here and absorbs moisture and temperature, probably going to float somewhere between 50 and 60% relative humidity in the space. But what if I need to be down around 30% or 40% relative humidity? Then what I have to do is I have to continue to cool that air further sensibly so that I can remove more moisture over here on the right-hand side, more grains per pound. So maybe I need air coming out at, say, 45 degrees Fahrenheit, 45 degree wet bulb, 45 degree dew point, so I can hit that 30 to 40% relative humidity in the space. Or let's say that's not enough. Let's say I need to be down around 10 or 20 or 25 or 30% relative humidity. I have to then continue to chill this air further and further and further. I have to continue to deeply cool it in order to drop its temperature, drop the surface temperature of the coil, drop the temperature of the leaving air, and condense more moisture out of it. It's the only way I can accomplish deeper dehumidification with a system like this. Colder surfaces, colder fluids, colder leaving airs, etc. Right? Now, the problem with that is simply that if I have chilled that air so far that when it is put back out into the space, it creates an uncomfortably chilled space, then I have to do something to that air to warm it back up. I've removed the moisture, that's great, but I now have to add sensible energy to this air and maybe warm it from 40 up to 55. So I've got 15 degrees of reheat, right? And that can be very inefficient and unsustainable. if I'm using new energy to provide reheat. So that's a problem with regards to this type of a system, a cold coil system. The other problem is simply this. What if I need to be around 10 or 20% relative humidity or less? I have to continue to drop the temperature of that air, but I can only drop it so far. And here at 32 degrees Fahrenheit, the train comes off the tracks, right? If I create a cold coil surface temperature of 32 degrees Fahrenheit and the moisture in the air is condensing onto that surface, it begins to frost, it freezes, I create a block of ice, and I get no airflow. And that's a problem. So in situations like that, where I have low relative humidity requirements in the space, and I cannot achieve enough moisture removal with a cold coil surface, I have to use something that will remove moisture from the air without condensation, something that will hold moisture as a molecule, never letting it get wet, never letting it condense, so that I can pull the moisture out of the air, but I don't have issues with condensate freezing. And you know what? Silica gel. Desiccant dehumidification is a perfect way to accomplish that. And we'll talk more about that in a minute or two. One thing I want to point out, here's a little psychrometric bonus trivia for you today. Did you realize that when you take warm and wet air through a coil and you condense it onto this coil surface, you are actually putting sensible heat back into the air? Anytime you have a phase change where you take gaseous moisture and you condense it, there is a conversion of latent heat to sensible heat at the rate of 1,060 BTUs per pound. And that conversion of latent to sensible is imparted to the airstream. And this air leaving the coil actually instantaneously warms up quite a bit in actuality, but we never see it. We never know it's there. All we know is that I have cold and drier air leaving this coil. Where'd the heat go? Well, because the coil surface is cold, that sensible heat is immediately absorbed into the refrigerant or chilled water, and it's dissipated outdoors to the cooling tower or to a condenser or whatever the case might be. But this is called the latent heat of condensation. And it's very important to understand that it's there. Although we don't recognize it or see it, it's a part of psychrometrics. It's just the way it works. Right? And I want you to be aware of that when I start talking about how desiccants work. This is going to be a very important topic for us to come back on in just a slide or so. I think the next slide. All right, here we go. So here we go. Typical solid desiccant dehumidification system, if you will. It looks weird, you know. It just seems weird. And while it may seem weird, again, as I mentioned, it's thermodynamically eloquent, incredibly efficient, and sustainable done right. Let's talk about it. Also looks a little bit like an energy recovery unit, doesn't it? You got a wheel, you got two air streams, you got stuff going on. It is not an energy recovery unit at all, okay? Big difference. And I'll talk about what some of those differences are as we move forward, but I want to make sure you understand it's not an energy recovery unit. It is a industrial grade commercial desiccant dehumidification system. Now I do have two airstreams. We will talk quickly about this upper airstream and then I'll come back to it. This is my oven. This is how I dry it out. Okay, we'll come back to that in a minute. On the lower portion of this drawing is what I'll call my process airstream, or the airstream that I want to dehumidify. Now, in the center of these two airstreams opposing one another, never letting these two airstreams come in contact with one another based on seals, right? We don't want any cross-contamination. I have in the center of a wheel a substrate material with flutes in it. Our substrate material is fiberglass. This wheel is about 12 inches thick. This wheel rotates at about 8 revolutions per hour, and this fiberglass substrate material is incredibly durable. If you go up and hit it with your fist, you are going to hurt your fist. You're not going to hurt the substrate material, nor will you dislodge any of the desiccant material that has been bonded to this fiberglass substrate material. Now, again, I mentioned it's fluted. Air flows through it in two directions. Our process airstream coming in can be 100% outdoor air. It can be 100% return air. It can be a combination of outdoor air and return air. It can be air as wet as you want to bring into that unit. The sky is the limit. You just can't stick a garden hose in the back end and get the wheel wet. The wheel needs to stay physically dry, and it always will, done right. Okay? I take this wet air that I want to process and dehumidify through a filter of some type. Our units can accept MERV 8s up through MERV 16s. On the inlet side, we can do HEPA and ULPA filtration on the discharge side, should you want it. But I then may run it through a pre-cooling coil, depending, but sometimes not. And as this warm, humid air filled with moisture at a high grains per pound level flows through these flutes and comes in contact with the silica gel material, which has been embossed into the substrate material. The silica gel, because it's dry, is at a very low vapor pressure. And just like the silica gel in the box, it is able to adsorb or suck the moisture out of the air in this high moisture level airstream coming in and hold that moisture as a water molecule in the pores of the silica gel, never condensing, never getting wet. The wheel is always dry. Okay, leaving the wheel then is air that has been dehumidified, perhaps deeply dehumidified. Perhaps the air leaving here is at a fraction of 1% relative humidity, if that's what you need. Lithium battery manufacturing, for example, we're providing negative 80-degree dew points. That is incredibly dry air. You have to in those environments. Any environmental moisture in the air at more than a single-digit relative humidity in the space will react with lithium. It will create a corrosive response that combusts and you blow things up. You can't do it. Lithium battery plants use desiccants all the time. But the point is, it can be as dry as you want it to be. It doesn't have to be that dry. And what will determine how dry this wheel is and how much moisture it can remove and the relative humidity or dew point that you can get down to on the process leaving side is the heat source. The more heat, the drier the wheel. We'll come back to that in a minute. Now, this air has also been warmed up. So it leaves the wheel warm and it leaves the wheel dry, perhaps incredibly dry. The air here may leave up to 100 degrees Fahrenheit. It just depends, right? That is the latent heat of adsorption. It's very similar to the latent heat of condensation that I mentioned occurs in traditional cold coil systems. It's just I haven't taken it out of the air yet. I've left it there. Now, if I want to, I can put a post-cooling coil right here, and I can cool that air down from, 85, 95, 100 degrees Fahrenheit, whatever it comes off the wheel at, depending, down to 55, 45, 35, 25, minus 25, minus 40. Doesn't matter. This air's dry. The coil that is in the process post-cooling coil position will run dry. It's sensible only. So I can have air as cold and dry as I want it to be. The sky's the limit. Boy, you can't do that with a traditional system, can you? That's pretty cool. That solves a lot of problems. But if I leave this heat in the air, I can use it to offset reheat. And it can be incredibly energy efficient, incredibly sustainable. And we do it all the time in hospital operating rooms, for example. And I'll show you a quick example of that in the slides that follow. So we've taken care of the process airstream. A lot of people look at the heat coming off the wheel. They don't understand that it's just a part of psychrometrics. They go, well, that is weird. That's not how we do it in traditional systems. Yes, it is. And it can't be energy efficient. And yes, it can. So we'll come back to all that. I promise to prove it to you. This is a great benefit to desiccants. All right, now I've loaded this wheel up with moisture. My desiccant is full of water molecules. Just like a sponge is full of water, my wheel is full of moisture molecularly. And just like my packet, I have to either throw it away or dry it out. So this wheel continuously loads with moisture and revolves into an opposing airstream. One thing I want to point out is that the reactivation airstream or my drying airstream or my oven is a smaller percentage of the total airflow based on the total diameter of the wheel. So what I'm saying is this is about 25% of the wheel's total airflow. If this was 1,000 CFM wheel, I'd have 750 CFM of process air and about 250 CFM of reactivation air. It's a smaller quantity. I can take that reactivation air from anywhere I want. Typically, I'll take it from outside just because it's easier. It's easier to get there. Doesn't have to be, but that's where we'll normally take it. And it doesn't matter how much moisture's in it. Sky's the limit. We don't worry about that. What we do is we take the proper amount of air through a filter, keep it clean, run it through a heat source. This is thermal energy. So depending on what the air is coming in at, and depending on how dry I want this wheel to be, I will have a leaving air temperature that I need to meet. This leaving air temperature can be anywhere from 100 degrees Fahrenheit to 300 degrees Fahrenheit. In lithium battery manufacturing, where I'm trying to garner a fraction of a percent relative humidity in the leaving air, it's going to be 300 degrees Fahrenheit. I got to have a really dry wheel to accomplish that. But that's not the case in most applications. Many applications you may see, I don't know, I can go anywhere from 150 to 225, 250 degrees Fahrenheit, typically, depending, right? And as this air that has been heated comes in contact with the substrate material, it heats the desiccant, heats the wheel a little bit, and it increases the vapor pressure of the moisture in the desiccant to be above the vapor pressure of the air in the reactivation airstream. And guess what? It desorbs, it spits loose the water molecules that were in that wheel, it dries the wheel out, and I then get rid of them outdoors. And as long as the wheel is turning, and as long as the fans are moving, and as long as this heater is working, I have dehumidification, right? I'm taking low vapor pressure silica gel, adsorbing moisture, rotating it into an opposing airstream, increasing its vapor pressure, desorbing the moisture, and the world is a beautiful place. And it just is so efficient and so eloquent and works so well and is so simple when you understand what's going on, okay? Now, this heat source is thermal energy. Thermal energy. I have to have an input. There is no free thermodynamic lunch. And I'll talk more about that in the next slide. But this heat source can be electric. It can be gas. It can be steam. It can be hot water. It can be waste heat. If you have waste heat at the right temperature, dehumidification is basically free. This is the largest energy consumer in a desiccant dehumidification system. It's this heat source, right? So the parallel I want to draw is between my thermal energy input and the energy input required to drive a more traditional dehumidification system or air conditioning system, right? Now, as I mentioned, there is no free thermodynamic lunch. I have to create a thermodynamic difference between indoors where I want to remove something and outdoors where I want to get rid of it. I have to create lift between the indoors and the outdoors. I do it with heat, with thermal energy. Gas, electric, steam, hot water, waste heat, doesn't matter. I have an energy input. Just like its counterpart, let's take a chilled water system, for example, requires electricity to run a compressor, to run pumps, to run a cooling tower and fans, and create lift between indoors and outdoors to get rid of what I have absorbed in the cooling coil and discharged through the cooling tower. So this is not inefficient. It's not weird. It's not an unsustainable way to drive this system. In fact, it's very efficient, very sustainable, and it parallels exactly what we have to do in more traditional systems. So now that you've understood how it works, you see heat down here in the process airstream. It's not weird. It's just a part of Psychrometrics. It's in this other system as well. We just don't see it. And you see heat up here, which isn't how we do it in a traditional system. Well, no, not necessarily, but I have to have an energy source. And heat is my energy producer, if you will. I have to have thermal energy. Down here, I have to have electricity that drives these components and creates lift. Same thing, right? So hopefully I've dispelled any myth that you might have that desiccant dehumidification is anything other than efficient, sustainable, and effective. And it most certainly can achieve outputs way beyond what more traditional cold coil systems can produce from a dehumidification perspective. Let's keep going. Psychrometric chart. Hate to do this to you. When I first started in this industry, I had a mentor. He said, you're going to be doing lots of presentations for people. You're going to have to talk about psychrometrics. But my first rule of psychrometrics is never talk about psychrometrics. But I have to, and I think this group will appreciate it and understand it. So I show a psychrometric chart, and I show where desiccant dehumidification plays, where refrigeration, cold coil systems play, and this gray area between the two. There's always a gray area. So let's unpack this a little bit. Here's my general rule. If the space conditions need to be maintained at a dew point temperature below 50 degrees Fahrenheit. What's that mean? Here is a 50-degree dew point temperature right at the top of this gray line. We see 50 on the left-hand side. We see 50 on the right-hand side. That's a 50-degree dew point. If the space needs to be maintained at a dew point temperature less than 50, or the delivered air dew point to the space must be 45 degrees Fahrenheit dew point temperature or less. And that's right about in the middle here where you see the yellow line begin. If it's either of those or more stringent, you should probably be thinking about desiccant dehumidification. And in fact, if you're much more stringent down here in the yellow area and 2 psychrometric charts off to the left down to about negative 90 degree dew point temperatures, solid desiccant's your only solution. It's the only thing that'll work, right? But if you're up here and you're at, 70 or 75 degrees Fahrenheit and 50 or 55 or 60% relative humidity, traditional refrigeration systems, cold coil systems play well. Let the plumbers plumb. I got no problem with that. Tracy and gang have all kinds of solutions that are very cost effective, very efficient up here in the red area. But sometimes these systems overstep their bounds a little bit. They try to do a little bit more than they should or could. There may be reasons. Maybe it wasn't designed quite right. Maybe the equipment's getting older. Maybe the space has been repurposed and it requires lower relative humidities. And you don't want to throw the baby out with the bathwater. You'd like to use this system if you can. Maybe it's brand new, just can't hit the mark. Well, what I can do with desiccants is step up and make traditional refrigeration-based systems play in the gray area. Right here, where they really can't perform alone. But if I help them, if I take a little bit of the load off of them, I can create a hybrid system that will very efficiently and effectively, and most certainly first cost effectively, play real well right down here in this gray band. And we do this all the time. Do it all the time in hospital operating rooms. I'm going to show you a quick example of that in the slides that follow. But it's important to understand that down here it's me, up here it's them, and right here it's us, right in this gray area. It's going to be us, and we do all kinds of jobs. In fact, I'd say 50% of the jobs that I do are in the gray area. 25% more are a combination of new jobs where I'm playing in the gray area because I'm using desiccants and traditional solutions to make a more cost-effective package for the owner. And then another 25 or 30%, whatever, are down here where it's strictly desiccants because it just makes more sense. Okay, we'll come back to that in Q&A should you want to. I'm going to talk about some of the markets for desiccant dehumidification. I have 3 slides. I have several examples. I don't hit them all. There's so many more, but let's talk about a few. Food processing, it's always wet. It's always cold, always refrigerated temperatures. You always have stuff that's icing up and getting wet. Desiccants most certainly can help solve those issues. Pharmaceutical manufacturing, where you're maybe manufacturing gel caps that need to be dried, or you've got powders that are hygroscopic that need to be shoved into those little gel caps. It's real important to maintain low moisture quantities in those spaces. Laboratories, colleges, research facilities, electronics manufacturing can't have any microscopic condensation on those circuit boards, or you'll lose millions of dollars of product just like that. Automotive industry, hospitals, I do lots in hospital ORs. It's the easiest lifting of all the vertical markets that I've shown here, but we'll talk about an example that plays in the gray area that I think you'll enjoy. Aerospace, where you're trying to create, this shows airplanes, I don't like that. Rockets, missiles, satellites, where you're trying to create test environments that replicate the amount of moisture in outer space. You've got to have desiccants for that. Plastic injections, military, you've got metal, you've got electronics, they need to be dry. We do tons of military stuff. Archival storages, museums, books, libraries, things like that. Glass lamination. Grow facilities, doing a lot in the cannabis market. Plants are always spitting moisture into the air. They always transpire, lots of moisture, lots of issues with mold and mildew, and water all over the place. Desiccants are a great solution there. And then, of course, ice rinks. That's just a no-brainer. Ice rinks aren't always done with desiccants, but the ones that work well are. I'll leave it at that. I say anywhere moisture in the air or on a surface negatively impacts the environment, the product, the process, the outcome, the comfort, or the safety of occupants in the space is a potential application for desiccant dehumidification, and the vertical market applications are endless. If you've got others, I'd love to hear it in Q&A. I took out the slides. That's okay. We'll come back to that. I dropped the slides on the hospital operating room that I wanted to show you. I can come back and open that up if we have anybody that's interested in hospital ORs or working that gray area and taking systems that don't work and making them work. I can come back in Q&A and open that up. I apologize. Real quickly, a little bit about our products. We start with a small series that we call compact. It's compact because it's small. They're available in increments of 75, 150, 300, and 600 CFM. And everybody goes, gosh, how much moisture can you pull out of 600 CFM of air? Well, a lot. When you deeply dry it, I might be able to pull 25 pounds of moisture an hour out of a small 600 CFM airstream. That's a lot of moisture out of the air. This unit comes in stainless steel. It can be installed indoors. It can be installed outdoors. It comes with the process fans. It comes with the regeneration fans. It comes with the filters that are required. And it comes with an electric heater. So it's totally self-contained. All of our units are driven by a chain. You see the chain drive and motor rotor assembly here. It's a little more robust on the bigger units with the bigger wheels, but the point is no belts to slip or break. We're very proud of that. We build a very high quality product that's built to last and be durable. This shows an example of a couple of, I think, 75 CFM compact units provided on a freezer storage facility. So let's think about this for a minute. Let's say this is being maintained at, I don't know, 0 degree Fahrenheit. It doesn't really matter. And you've got some type of refrigeration evaporator in here that's attempting to maintain 0 degree Fahrenheit. What happens every time you open this door to go in and get something out? This warm, super moist air will rush in and it will hit those cold surfaces and it will immediately turn to frost. It will do what's called deposition. It will go from a vapor to a solid without condensing. And everything ices up over a period of time, including the evaporator inside this unit that's having to condense that moisture that comes in. You know, it's putting out minus 10 degree air to maintain a 0 degree Fahrenheit environment. So it's going to frost and freeze almost immediately. And in fact, many times you'll have two evaporators in there. And when one frosts or freezes up, you turn it off and defrost it and turn the other one on. Well, what we do with desiccant dehumidification is to provide very dry air to these environments at a low enough dew point temperature that it will actually sublimate the moisture out of the ice into the air. It will pull the moisture out of the ice without having to condense it, sublimate, and help keep these environments dry. Really cool stuff. It's amazing what you can do with these. But that's just one example of where we apply these smaller units from 75 up to 600 CFM. As well, many times we would take an ailing-failing system. Let's just throw a number out there, 7.5 ton packaged rooftop, doing an environment, maintaining the space, on a design dehumidification day at 65% relative humidity. Nobody's very happy. We may take these small compacts and based on a small quantity of air, pull some air off the return, drive the living heck out of it, shove it back into the return of this existing ailing-failing system, and make it more of a dehumidifier. Take the dehumidification capacity off of this unit so that now all it has to do is respond to a sensible-only cooling thermostat and maintain space comfort temperatures while this is responding to a dehumidistat in the space and is doing the dehumidification. And maybe now that space that at best could do 65% relative humidity is now able to do 50% relative humidity. We do this a lot. So it's just one way to skin the cat. This might not be a small system either. I've done some side stream applications where the dehumidifiers are 10,000 CFM and we're fixing huge systems that aren't working well. We can do that kind of stuff. We can also provide this as a DOAS and simply dehumidify all of the ventilation air coming to the space, handle the entire outdoor air latent load and the indoor latent load, and then make whatever it's feeding downstream sensible cooling only, maybe sensible cooling, heating, filtration, humidification, whatever. Just a great way to optimize the system from a first cost perspective and get the results that you want. Playing in the gray area, sometimes even lower. And from there, 600 CFM and above, we go into what's called our rotor series. We go up through 30,000 CFM with these units, indoor, outdoor, can have pre-cooling and post-cooling and preheating and post-heating and HEPA filtration and bypasses and humidification. We can put air-cooled or water-cooled condensing units on them and give you a packaged solution, perhaps a DOAS, whatever the case might be. Sky's the limit, as big as you want. These are what we might provide in battery manufacturing plants, pumping out close to negative 80 degree dew point temperature air, as an example. I'm going to leave this on the screen real quickly. Should anyone want to scan this QR code with their phone, it will take you to take you to this. This is what you're going to see, and it will allow you down here at the red arrow to save this to your phone, and it will give you a cover app for it. You can also download this to your laptop should you like to. And this is, for my money, one of the best free psychrometric tools in the industry. There's all kinds of things you can do. You can do psychrometric state points. You can get weather data for all the ASHRAE weather stations in the US, Canada, and Mexico. You can do mixed air calculations. And once you're up to speed, you can actually select a desiccant wheel yourself. I use this 10 times a day. Every job I do, I'm either pulling it out on my phone or pulling it up on my laptop. It's great for making engineering calculations, and that's our gift to you, if you will. This is our brochure. Should you want to scan that QR code quickly, it will take you to our brochure and let you look at a broader array of products and solutions that we have to offer. Our benefits, we feel our value proposition that we give to Tracy and team, and they in turn impart to you, is that we're very competitively priced in the desiccant realm. We're very attentive and relational. I'm 9 out of 10 times involved in every job from a engineering perspective, doing selections, doing submittals, and making sure it's going to work. We're flexible. We'll consider anything. It's only money. Whatever you want to do, we can do. I'll try to push you towards a direction that might make a little more fiscal sense, but the bottom line is, sky's the limit. We're custom, responsive. We pick the phone up when our reps call or when you call. Our lead times are the best in the industry, and we're 100% American made. God bless Georgia. God bless America. And this is me. This is my contact information. This QR code will take you to my LinkedIn site. I'd love to have you reach out and we'll become friends or connections. I post a lot of stuff. I do a lot of stuff on dehumidification. I do a lot of stuff on psychrometrics, a few other things. I think you might enjoy it, and it's just a way to keep in contact with me. But Tracy and team know how to get a hold of me. You most certainly can call me as well, should you like to, and we'll all work together. So with that, Tracy, I think I'm ready to open it up for Q&A if you're ready to allow